Don't speak. few minutes.
போட்டிருக்காங்க. ஆமா அது நிக்கி ஒரு இது போட சொல்றோம். மேடம் நிக்கி ஒரு இது போட got message from tenant. செக் நீங்க பண்ணி சர்ப்ரைஸ் ஆயிடுச்சுங்களா? ஓகே சார்
Yeah. Yes, please.
Chat. Message, chat message received.
Nikki, can we start?
Yes, let's start.
Can we start, Nikki?
Yes. Can you hear me?
Okay.
Okay.
Yes, Nikki. So we will start the proceedings right away. So Abhirami, the MC, will start now. Nikki, can you please unmute? Can you please unmute Abhirami VS? Hello. Hello, Nikki.
Hello? Oh, okay. So I think one sec. I'm asking her to unmute. Okay, there we go.
Sure, thank you. Abhi, start.
Greetings to everyone. I am Abhirami, student volunteer from Explore the Space, and I will be your MC today. We have all gathered now to participate in the second edition of the webinar series on future of space technology and exploration. This webinar series is being jointly conducted by Explore the Space and Elcon Precision LLC. Explore the Space is an educational NGO registered in the DRDO, Government of India, and works to promote awareness on space sciences and technology among schools and colleges, seminars, quiz programs, study tours and research, connecting institutions and industries through its programs. Elcon Precision LLC is a leading supplier of precision components for space-type applications, employing comprehensive expertise in engineering, material science, manufacturing, and assembly services for mission-critical projects. Through their systematic approach, process control, and careful engineering, they are able to produce parts built to succeed in space, which, as we know, is one of the most extreme environments. The space industry has reached an inflection point, and we are going to see a burst of activity both in the upstream and downstream activities. This is going to create a great deal of opportunities for the space industry. There is a growing need for skilled and talented professionals. There is a growing need for skilled and talented professionals in the space and allied industries. Colleges need to prepare their students to make the best use and gain advantage of this development. ETS will be glad to offer its support and assistance to the educational institutions in this process. The excitement that space technology provides is matched with unfolding opportunities that it is creating for new jobs in the space and related sectors. The modern lifestyle and advanced technologies have given way for very many options to pursue a career in space. Space vehicles, disaster management, weather forecasting, satellite navigation, global communications, etc. The space industry has plenty to offer. The participants in today's webinar are college students heads of departments and placement officers from colleges and universities from all over India, Uganda, UAE, and USA. We have students from the following streams: physics, chemistry, various branches of engineering, MBA, law, etc. We also have entrepreneurs and established companies who have joined us today and representatives from schools, including students and teachers. I now pass on the mic to Mr. D.V. Venkatagiri, CEO, Explore the Space, to deliver the welcome address.
Thank you, Abhirami. Nikki, am I audible?
Yes, yes, you are audible.
Greetings to all participants. Explore the Space in association with Elcon Precision LLC is very pleased to welcome you all for the second edition of the webinar series, Future of Space Technology and Exploration. Just to recap, we had the first edition of the webinar on 25th June 2021, about 2.5 months back, when the Consul General of India, San Francisco, Dr. P.V. Nagendra Prasad, inaugurated the webinar. And we had the keynote address by Mr. Tim Dyer, President of Elcon Precision. We also had an illustrious panel comprising Mr. L.K. Sharma, President of Indian Ceramic Society, and Mr. V. Ramamurthy, retired scientist, ISRO. Ladies and gentlemen, we have a very, very illustrious panel today with the webinar to be inaugurated by Her Excellency Ms. Grace Akello, High Commissioner of Republic of Uganda to India. And the keynote speaker is Dr. Jaideep Mukherjee, Director of Florida Space Grant Consortium, a great friend of Explore the Space for many years. Mr. Ed Tomasek, Director, Business Development of Elcon Precision LLC. We also have Mr. Sudhir Kumar, the Director of Capacity Building of ISRO, who has kindly consented to give us special remarks today. We have Mr. Balagurunathan, eminent science writer and Times of India awardee, and Mr. Manoj Pillai, advocate from Supreme Court of India, along with Ms. Akriti Singh, a student representative from Dubai, UAE, who will be making the remarks. Friends, the objective of Explore the Space, along with Elcon Precision, in doing this webinar series is to encourage the youth across geographies, across continents to take up space sciences as their career. That's objective one. And then to promote industry institution partnerships in the space industry. And finally, the third and important objective is to emphasize global cooperation in the space segment. With those three objectives, Explore the Space and Elcon Precision have launched this webinar series. I am now pleased to introduce to the audience Madam Grace Akello, Her Excellency Ms. Grace Akello, who has very kindly consented to inaugurate the webinar today. Madam Grace Akello is currently Uganda's High Commissioner to India. Prior to this, Madam Grace Akello served in the Republic of Italy, accredited to Greece, Malta, Cyprus, Albania, Bosnia, Macedonia, and Slovenia. Madam Grace Akello was the permanent representative of Uganda to the United Nations Food and Agriculture Organization, FAO, World Food Programme, and the International Fund for Agricultural Development. Based in New Delhi, Ambassador Akello is Uganda's envoy to India and the Southeastern Asian countries of Nepal, Maldives, Sri Lanka, Bangladesh, and Singapore. In her dedicated service spanning over 45 years, Ambassador Grace Akello has served in various capacities in government of Uganda, including as Minister and Member of Parliament, and in other global platforms such as the Commonwealth Secretariat and the East African Community of Kenya and Tanzania. We have pleasure in welcoming Madam Grace Akello. May I now request Madam Grace Akello for her inaugural address, please. Over to you, Madam Her Excellency Grace Akello. Thank you.
Hello, can you hear me? Can you hear me? Okay, very good. So now, Mr. Venkatagiri, Chief Executive Officer, Explore the Space and Global Trade Driver, Chennai, India. Dr. Jaydeep Mukherjee, Director, NASA Florida Space Grant Consortium, Florida, United States of America. Mr. Sudhir Kumar, Associate Director, India Space Research Organization. Mr. Ed Tomasek, Director, Business Development, Elcon Precision LLC, San Jose, California, United States of America. Mr. Manoj Pillai, Advocate, Supreme Court of India and patron of Manocha Lab. Mr. Balagurunathan, science writer, an awardee of Times of India. All our distinguished members of the virtual audience of this webinar, ladies and gentlemen, it gives me immense pleasure to inaugurate the second edition of the International Webinar Series on the future of space technology and exploration, jointly organized by Explore the Space, an international organization working on space education from Chennai in India, and by Elcon Precision LLC, an American aerospace company that does business directly with the country's National Aeronautics and Space Administration, better known to the world as NASA. I am highly honored to inaugurate a webinar at which the eminent NASA scientist, Dr. Jaydeep Mukherjee, is the keynote speaker. Dr. Mukherjee will speak on NASA's Artemis mission, humanity's return to the moon. If I may indulge the audience a little bit, the last time that humanity touched the foot, put their foot on the moon, I was a 19-year-old teenager in a school in Eastern Uganda. And in excitement of the moment, we, the girls who were in an American built school in Uganda, invented a dance called the moonwalk. So we did our dance called the moonwalk in celebration of Neil Armstrong landing on the moon. So therefore, we are all eagerly waiting and looking forward for Dr. Jaydeep Mukherjee's presentation. International cooperation in space exploration has the potential to provide significant benefits to all participants, particularly if managed well. Benefits in the form of monetary efficiency, programmatic and political sustainability, and workforce stability will accrue to those partners who choose to approach space exploration as a mutually beneficial endeavor. Although my continent, Africa, is a latecomer to space exploration, the continent's space programs are becoming very popular. 21 years after the first African satellite, SANSAT-1, was launched into space by South Africa in 1991, the industry has been accelerated with hundreds of millions of US dollars invested into it. The last 4 years have been very successful space exploration years for Africa. Can you hear me? I hope you can hear me. A total of 20 satellites have been launched by African states since 2016, giving the continent her current total of 41 satellites. Egypt leads the way with 9 launched satellites, followed by South Africa with 8, Algeria with 7, Nigeria with 6, and Morocco with 3. Ghana, Sudan, Ethiopia, Angola, Kenya, Rwanda, and Mauritius complete the list. To this, we can add 3 geo-telecommunication satellite multilateral projects. 2 of the geotelecommunication satellites were launched under an agreement with RASCOM, the Regional African Satellite Communication Organization, representing the interests of 44 African telecommunications operators, the first African telecommunication satellites covering the whole continent. The third satellite in question is New Dawn, built for Intelsat and convergence partners. Ladies and gentlemen, allow me to speak briefly on the benefits of space cooperation. The use of space science and technology could be of benefit to all of us on planet Earth. Key among these planet-wide benefit areas are aviation, maritime and land transportation, urbanization, mapping and surveying, human health, disaster management, food security and sustainable agriculture, environmental monitoring, and natural resources management. Distinguished ladies and gentlemen and panelists, space science and technology can help humanity in 1, protecting our planet and our environment. 2, enhancing the safety of planet Earth. 3, improving our day-to-day lives, which is at the practical level here. 4, improving healthcare. 5, in creating scientific and technical jobs. 6, in making scientific discoveries. 7, in sparking in our youth, our young people, the next generation of humanity, a dynamic and continuous interest in science. And last, and perhaps most important of all, space science and technology can help humanity enhance global cooperation for the common good of planet Earth. The benefits of space can be categorized as either direct or indirect. The direct benefits of exploration include the generation of scientific knowledge, the diffusion of innovation and creation of markets, the inspiration of people around the world, and the agreements forged between countries engaged in exploration. Distinguished audience, as I draw to the end of my inaugural speech, allow me to share with you some elements of Uganda's nascent space program. Uganda is venturing into the field of space exploration and technology, aiming to launch its first satellite into outer space by 2020, next year. Next year, we shall be there. The country revealed this stage in her space exploration venture in an announcement made by the Ministry of Science, Technology and Innovation in November 2019. The project is now taking shape based at Uganda's Earth Satellite Station grounds in Mpoma. I'm glad there is an Ugandan audience so they know what I'm talking about. It is clear that the country is looking forward to the success of this emerging industry as she expects the project to bring many benefits to the Ugandan economy and to many areas in the well-being of her people. Communication satellites, which are the building blocks of broadband telephony, internet and TV, to remote sensing satellites, have greatly improved the weather prediction process in Uganda and have provided people with early warnings of dangerous weather conditions. Ugandans are increasingly using satellite devices and applications, from global positioning systems, GPS, for enabling an individual with a GPS device to know an exact location of interest, to agricultural applications for improving health services and education. Ugandans recognize that space technologies are vital components of the modern information society. Therefore, Uganda keenly embraces space-related education platforms and will attract college students and professionals, such as I hope are among our audience tonight, to participate in them and in subsequent steps in the exploration of space and its associated technology. In line with the Space Generation Advisory Council, Uganda's objectives are: 1, to encourage and engage the youth of Uganda to be part of the space initiative. 2, to create activities such as Yuri's teleconference, our World Space week to promote space science to students. 3, to promote a dynamic forum for members to participate in active discussions and expand their knowledge. And to collaborate with other national bodies on regional issues, as well as the Global Space Generation Advisory Council Network. Distinguished panelists, ladies and gentlemen, I wish the organizers of this program all success as they continue with this series of webinars to promote scientific space education among the youth of the world. I thank you very much for your attention.
Thank you so much, madam. Thank you, Madam Grace Akello. Her Excellency, Madam Grace Akello, for your inspiring inaugural address. Over to Abhirami. Nikki, can you please help Abhirami to unmute?
Yes, I am. He should be co-host right now.
Yeah, Abhirami.
Yeah.
Abhi, try. Thank you.
I now request Mr. Manoj Pillai to introduce Mr. Ed Thomas. Thank you.
Thank you, Abhirami. I have the great privilege of introducing Mr. Ed Tomasak, who is the Director of Business Development of Elcon Precision LLC USA. When you talk about a director who is taking care of business development, that means a person who has got a lot of expertise how to develop a business. And we all know we are looking at the space as one of our business destination. So I would be great if I'm able to make a comment about Mr. Ed Tomaso, who's a person of so much of entrepreneurial skills to enlighten us with his expertise and how his company, Elcon Precision LLC, has been working hand in hand with NASA and how he has been helping entrepreneurs like us who want to make space as our business destination. I would request Mr. Ed Tomaso to take over and enlighten us with his special address. Over to you, Mr. Ed Tomasak.
Thank you, Manoj. My name is Ed Tomasek. I'm Director of Business Development here at Elcon. And I'm gonna, I guess, first of all, I'm just in awe of the reach that we're having here from Africa to India to the United States, and really appreciate DB setting this whole thing up. I know it was a lot of work, but so I'm gonna go through fairly quickly what kinds of things Elcon does in terms of manufacturing, and then I'm going to move into some of the projects that we've done with both academia and with NASA and other companies involved in space. So I'm going to turn my camera off and start the presentation. Go. So Elcon Precision is, we're located in San Jose, California. We were founded back in 1967. We have 51 employees now, and we occupy 34,000 square feet. We've got a lot of certifications that relate in many ways to space. AS 9100, which is an aerospace certification, ISO certification, RoHS, which is making sure that we're not using unsafe chemicals and elements. And we are also ITAR registered, which is important for doing business here in the US. We have multiple markets, biomedical, electronics, commercial, and defense and aerospace. You can see there all the kinds of things that we make. And we're always looking for new things. We get projects thrown at us that look like they can't be done, but we're always willing to look at it to see if we can make it work. We have two divisions, the metal products division and the ceramic product division, and I'll go through them each separately. So metal products division, this is mostly photochemical etching of a wide variety of refractory and other metals. You can see all the metals on the left. The first three are actually, or the first four are actually refractory metals, titanium, tungsten, and moly, and hafnium. But we also do other common metals like copper, iron, nickel, and others. And this photochemical etching process allows us to make detailed features by precisely controlling our subtractive and additive processes. So on the lower left, you can see some very small components. These are roughly the size of your thumbnail. And we can also shape things, parts on the right, roughly the same size, but they're formed into a hemispherical shape. The technology is, it's a burr-free, stress-free process where metal is precisely removed to create a component using photolithography that images a pattern onto the metal. So we put photoresist on there, we image with light, we cure what's been imaged, and then what's left is a pattern, and then we etch away what's not covered by the pattern. It's known by some other names as well: chemical milling, photo etching, photochemical machining, and some others. So if you see these other names, it's all the same thing. Large range of materials that we etch: moly, tungsten, titanium, hafnium, which are all refractories, pure metals, copper, nickel, palladium, and then some other alloys that you can see there. And we can also selectively plate. So using the same photolithography process, we can also plate where we want to, and we can combine or make separate gold and silver and other plating metals on a part. So we have several medical customers that require both nickel and gold on their part, but in separate areas. So that same process this allows us to etch also allows us to do that with plating. These are many examples of parts that we make. Just in general, the parts on the left, those are used a lot in RF technologies, radio frequency technologies. The part right in the middle at the top, that's that gets formed into a needle-like component that actually goes in a headband that attaches to your brain and reads signals from your brain. So the very little tiny tips on there penetrate just enough of the skin to read signals from your brain. Below that, those are the round parts are hemispherical grids. Those are used in wave tubes that are used for communication, radar jamming, and other applications, both in space and on aircraft. And then on the right, you can see some form components where we etch first and then we form. And many of those are also RF, but we also have, there's an aperture there. And you'll see an even more sophisticated aperture later on when I talk about an application that's actually up in space right now. Our ceramics product division, we work with multiple ceramics, as you can see on the left side. And most of what we do with ceramics is metallization and brazing a metallized ceramic to metal to create precision brazed assemblies. So two products we make: precision metallized ceramic components brazed assemblies, either metal joined to ceramic or metal joined to metal. You can see all the materials we work with. The most common is alumina, which is aluminum oxide. It's a very heat resistant compound or structure that is good for, it's got a lot of electrical insulation and heat resistance, and it's a very common material. You see it all over the place. You may not actually see it, but it's inside of a lot of things. Primary markets are aerospace and defense, energy storage, and medical. So we make thick film refractory metal paints, and we paint those on to the ceramic, and this provides a reliable means to attach metals to ceramics. The metal paints are applied in various ways, screen printing, just painting with a brush, spraying, and we do that to the ceramic base, fired in our hydrogen furnaces at temperatures greater than 1400 C. So this combination of the paint, the ceramic, a high temperature braze alloy, and a metal part in a braze furnace creates an electrically insulated and hermetic bond. Next slide, I'll show you some parts that we can make doing this. So our paints enable metals and ceramics to withstand high temperatures and high voltages required for lunar and spaceflight applications. So that top picture, the little part in the middle, it's actually sitting on top of a US penny. So that's the actual size of it. That's a little X-ray tube that's got something like 12 or 14 components that we assemble in a fixture and then put into a braze furnace where everything is brazed together into one solid piece. The parts on the right, many of those parts are feed-throughs. Those are used in medical, space, aerospace, many applications. Down below, we also braze metal to metal, so you can see some tubes. That's for a medical application. And the large part on the right, you can't see the inside of it, but that's got multiple metal and ceramic to metal brazes in it. That's a high vacuum switch used in radar applications. This gives you a couple examples of how complex parts that we can make. The one on the left is that switch you saw on the previous page. On the top, there's a vacuum enclosure that has to be sealed, so it's brazed to be a hermetic seal. And then on the bottom part, those are all the mechanics of the switch. So what happens in simple terms is, I think I can show with my cursor. This is the switch mechanism. This is in vacuum, and these are the contacts. So this thing pushes up against here, and this is high voltage, high frequency switching. So if this were not in vacuum here, you would have a lot of corrosion and just erosion on these copper contacts as it made multiple fast switching at high voltage. This part on the right is a little X-ray tube. As I said before, there's something like 12 or 14 components. This is a sapphire rod right here that's brazed, or we also use a glass frit to attach it, but it's brazed to these 5 components here in 3 spots, here, here, and here. We make 3 of these components using etching, and then the other 2 are machined by an outside company. And then also these 3 legs are brazed together. So all of these components are put together in one operation in the braze furnace, and we do hundreds of these a month. And they're actually a replaceable part. They eventually will wear out. But very complicated assembly, and it's all done in one step in the braze furnace. So that's what Elcon does. And I want to talk a little more now about some partnerships that we have with academia and with the space industry. So University of Michigan, we provided conductor bus bars for their national champion solar car team entry. This is sort of a race across the country where the car can only be powered by solar panels on the rooftop. And this team has won the championship multiple times. So we're proud to be a part of that entry. Fermi Institute in Chicago, University of Chicago. We made some sensors that were particle detectors. These are used in security devices and in other places. They're not terribly large, maybe 2 to 4 inches square, but a very complicated assembly that we are happy to work with U of C on. UC Davis, we recently sponsored 2 teams of seniors for their senior projects. One is to characterize and reverse a problem we had with darkening of some aluminas during metallization. They came up with a solution. They worked on it for several months, and I believe they actually got the top prize for the senior project that year. We also worked with another team on the ductility of thin metal sheets during forming. We have to form parts once we etch them, and it takes quite a lot of force sometimes to do this, and we have a problem with cracking sometimes if we go too fast or the material isn't of the quality we need. So they did a lot of work characterizing the ductility of these thin metals, and we're actually applying some of their results now for some of our customers. Our president is a member of the UC Davis Materials Engineering Advisory Board. He's also a graduate of UC Davis from the engineering school. With Stanford University, we worked on the SLAC, which is the linear accelerator, multiple little parts for that. And with Cal Poly San Luis Obispo here in California, we had students come in and another senior project, redesign our stock room, and much more efficient stock room. I wish I could show you the before and after pictures. The before pictures are rather embarrassing, but the after pictures are just terrific. So moving on to partnerships with the space industry. With SpaceX, I can't really show you what these parts are, but we have components up in the Starlink internet satellites. There's probably 1,000 up there by now. With NASA, we have components on the Ion engine, on the DART, which is the Double Asteroid Redirection Test mission. This thing is set to go into space sometime late 2021. The window opens in November, and then whenever they're free to launch, they'll put that into space. We also made grid plates for one of 10 instruments in the solar orbiter, which is up there now, launched in February 2020, and it's actually coming close to the sun and sending back information now. I'll show you pictures of both of these projects in the next couple slides. We also work with Space Foundry. We provided them with incubator space and infrastructure. They make plasma jet 3D printing for space. And this 3D printing is going to be very necessary and very important if you're going to manufacture on the moon. It's extremely expensive to send things up to the moon. So it's much better to send the much lighter components, which take up less room, and you can send them up in multiple missions and then manufacture up on the moon. So 3D printing is very important, and with very low gravity, this plasma jet printing is an important component of that. So this is the DART mission. NASA is sending this satellite up to this binary asteroid, and it's going to slam into the smaller of the two. It's sort of a moon. And when they do that, they will change the orbit of that little rock you see. And that in turn will change the orbit of the larger. And this whole project it's a proof of concept for any asteroids that might get loose and head towards the Earth. And then this would give us the opportunity to smash a spaceship into one as it comes into the Earth, and hopefully redirect it away from the Earth and somewhere where it's going to do less harm. It's going to take about 10 months for that spacecraft to get there. So towards the end of last year, if all goes well, you'll be hearing about this project and its hopefully successful conclusion. This is the xenon ion engine. So as this thing goes into space, it needs to accelerate. I don't remember the exact numbers anymore of how fast it's going, but it needs to accelerate to be able to have an effect when it slams into the asteroid. So we have two components on this. We have this electron gun right here, and we have this neutralizing electron gun. These are critical in order to ionize the xenon. Xenon is a very heavy gas, and you can accelerate these ions through this chamber here, and it comes out this grid, and as it goes out, it propels it. And then on the right here, this is actually the back end of what the engine looks like, and this is our little component up here at the top. So this is a fun project, went on for, gosh, over a year with NASA, and now it's on the spacecraft ready to shoot into the atmosphere. This is a project we did a few years ago. It's a pure tungsten piece. It's about 3.5 inches in diameter, and we made multiple parts like this, and then another company we were working with stacked them together to make this more solid part. And this is up there now on Solar Explorer, and it's used for imaging sunspots. So they can rotate this through here, and using diffraction and refraction, get different views of sunspots. Partly used because the sun is so bright, and you only really want to look at it through a slit and not directly on. We also make etched titanium, and this is important for electrolyzers. So when folks are on the moon, they're going to need fuel and oxygen, and both can be created from water in the form of ice found at the bottom of craters in the moon's south pole. You'll hear more about this in the next presentation. So we make titanium anodes, and they go over here, and you can, there's various forms of this. So these are stacks that are actually producing it here. This is the inside view, and these are different forms of anodes. So we hope to be a big part of this once things get on the moon, but it's just very expensive to be hauling hydrogen, oxygen, and other needs for living up there. So it's much better if you've got a source to make it while you're on the moon. That's it for me. If you have any questions, you can ask them later, but I will hand it back over to DV now. I think.
Thank you.
There we go.
Thank you very much, Ed.
You're welcome, DV.
Thank you, Ed, for that very interesting presentation about Elcon. Over to you, Abhirami.
May I now request Mr. Balaguranathan, science writer, to introduce Dr. Jaideep Mukherjee, NASA scientist.
Thank you. Mr. Balaguranathan, please.
Thanks for the privilege, sir. This honorable technocrat is the director of NASA, Florida Space Grant Consortium. This includes all Florida's community colleges, astronaut memorable foundations, Kennedy Space Center, Orlando Science Center. This consortium supports the expansion and diversification of space industry through providing grants, scholarships, and fellowship to the students and educators. Regarding his qualification, he received a bachelor degree in physics from St. Xavier College, Mumbai, MSc from the University of Mumbai, MS and doctorate from the University of Florida. Then he got a big ticket to NASA as an administrator, Florida Space Grant Consortium. Soon, he elevated to the level of director of the same consortium, also director of the Florida Space Institute from 2006 to 2011. He served as the chair of the Southeast Regional Space Grant for 10 states from 2006 to 2014. He is one of the members of the board of the directors of the National Space Grant Foundation from 2006 to 2008, then another spell 2012 to 2013. Currently serving on the board of the directors of the National Space Grant Alliance, and also he is a member of the Commercial Space Operation Advisory Panel at the Embry-Riddle Aeronautical University. Regarding his awards, National Eminence Award from India, Group Achievement Award from NASA, Goddard Space Flight Center for the excellence in outreach, Kerrick Prize from Astronomy Department, University of Florida for popularizing astronomy in 1993. As a co-author, he wrote a book, Closed Binary Stars, a pictorial atlas with Dr. Robert Wilson and Dr. Derek Terrell. Regarding his area of interest, binary stars and STEM educations are his primary focus. Regarding his sports activity, he is an avid cricket and tennis player. He is married to Sheila Malik, both resides in Florida area. Area of specialization is understanding binary stars, mass transfer, mass loss, and the formation of unusual close binary stars and space education. He is none other than our today's chief guest, Dr. Jaydeep Mukherjee. He is the director of the NASA Florida Space Grant Consortium. We wholeheartedly welcome, sir. Now we are handing over the floor to you, sir. Thank you, sir. Thanks for the privilege once again.
Thank you very much for the introduction, and thank you, D.V. Venkatagiri, for inviting me to this talk. And thank you for all the students all across India, Uganda, UAE, and the US. So I think this is a very exciting time for us because tomorrow we are going to have the first all-civilian crew being launched to space. And that'll be launched by SpaceX. We live in exciting times. And before I start my presentation, let me show you something. Just 2 hours ago, there was a launch of a big weather balloon carrying experiments from all across the nation. And let me share my screen and see if we can show you that. You can see my screen. Can someone do a hands up? A thumbs up? Can you see my screen? Someone just...
We see it.
Okay,
Right.
great. Thank you.
Right.
So this is
சொல்லுங்க.
actually a video feed from a weather balloon. It's a huge balloon.
பீரோ இருக்கா?
Um,
பீரோ
can someone
அப்படியே மாத்திட்டா plain room வரும்.
turn off your mic, please? Okay. So this is actually a live video feed from the weather balloon. It's a huge balloon. It's carrying about 10 or 15 experiments made by students across the nation. The one in the back over here, which says UNF, that's an experiment from Florida led by a faculty at the University of North Florida called Mr. Nirmal Patel. But I just want to show you that students get these opportunities to build payloads that they can either put in a weather balloon, or they can fly on a rocket or go to the space station. But this is live video feed from 30,000 feet up in the Earth's atmosphere. So what I wanted to talk to you about is something different, and that is, it's about the Artemis mission and the return to the moon. So I'll share my screen again and show you the presentation. Okay, there you go. So I'm going to talk about the Artemis mission and the return to the moon, because there is a race going on across the globe of who can go to the moon, and there are different reasons why you want to go to the moon. Some of them could be for technology purposes, some of them just to bragging rights, but most of them is for understanding better the moon, our solar system, and figuring out how we can live on the moon and other objects in our solar system. So I'm going to talk about why we're exploring, why do we explore space, talk about the moon, surface features on the moon, the formation of the moon, and the search for water on the moon, because that's very important if you want to have bases on the moon or settlements on the moon. Then I'll briefly talk about the NASA's Artemis mission, how we're going to go to the moon, what's different this time, how we're going to go there, and when we plan to go. And then, if I get time, I think this is one of the most important things that we have to worry about, is the moon dust. This is going to be a major problem for lunar explorers. It doesn't matter which country you're from. If we don't figure out how to mitigate the moon dust, we'll have problems. And finally, if I do get some time, I'll show you a couple of slides of the space technology needs, at least for NASA. So I always like to start with this slide. I know your students here from physics, chemistry, engineering, but I wanted to give you an idea of how insignificant we are. So we are currently on a 4.5 billion-year-old spaceship, which we call the Earth. Our spaceship is self-sufficient, it's organic, and it's very, very complex. We are orbiting a power source, which is 1 million times larger than a ship, and that power source is the sun. But we know that there are about 200 billion more such power ships, possibly with ships like ours around them, in a group called the Milky Way galaxy. We know that there are 40 such groups in a neighborhood, and we think that there are more than 200 billion so-called galaxies in our universe. So welcome to life, which is more exciting when you think on a larger scale. So you see how insignificant we are. We are a small, tiny planet going around a very average star, which is about one of 200 billion stars in our galaxy. And our galaxy is one of about 200 billion galaxies in a universe. And then now people talk about multiverses, but there can be more than one universe. So, it's mind-boggling when you start to think about all these things. One question that I get a lot is, why do we explore? Okay. So there are two types of exploration. One is we explore because we do not know what we will find. And when we see it, we'll find it. Now, for example, take Newton's laws of motion. do you find any new textbooks on that? No, because we do understand Newton's laws. It has been verified. But then take, say, a subject like consciousness. We don't understand that very well. And that's why there are so many books been written on it. So there are lots of things that we don't understand that we need to find out, and that's why we explore. Another reason we explore is because we want to test our hypothesis. And I'm going to show how we do it when I talk about the formation of the moon. This is the beauty of science. And I know I'm preaching to the choir, but science is such that, you can be wrong, but then you figure out why you're wrong, you modify your hypothesis, you come up with a new theory, you test it with observations. That's why the world has progressed, because we are looking into science. We're looking at data, we're looking at facts. Unfortunately, the world is fed with misinformation the last 10 years. With the advent of social media, a lot of misinformation is being spread around. And I would really urge all of these students not to please forward all those mails and all those links that you get from others, because 99% of them are false. Unless you know for sure it's right, you forward them. So I think we're having a major problem with people not believing in data and facts because of misinformation. So Her Excellency really gave a very good presentation of what we're exploring. I'll just touch upon it very briefly. So one is protecting and understanding our world. And Ed talked about in the NASA mission where they're trying to see how we can divert an asteroid if it is coming towards the Earth. There are various ways that we think we can do it. One of them is to change the orbit a bit. And that's what they're working on with the NASA mission. So we really need to understand how we can protect ourselves from asteroids. The second part, inspiration and exploration, is where you come in, where the students come in. We are doing this to inspire you to become scientists, engineers, doctors, lawyers, anything, but to inspire you and to explore. Her Excellency talked about the new technology that's been developed because of space, and I'll show you a couple of slides on that. A fundamental thing that humans have is that you want to answer unknown questions. We are always asking questions. And I always encourage students to ask questions because the only way we can go forward is being more knowledgeable. Finally, we have international collaboration. The only way we can go to the moon, go to Mars, go to an asteroid is to collaborate with various nations. No single nation can afford to really do it. So international collaboration has become important. And then long-term survival. Climate change is a major problem. We are almost gone beyond the stage we cannot go back and revert the climate change. So long-term survival requires us to understand more about other planets, how they were formed, and how we can use their knowledge to help the Earth. Here are the benefits of space exploration. As you can see, this is just a small part of it, from radiation blocking lenses to hip replacement, Velcro. Though Velcro was not actually invented by NASA, it was used by astronauts everywhere. Diapers, GPS, advances in heart pump, pacemakers, digital cell phone technology, and so on and so forth. I can go on and on about that. And this next slide, I won't go through it, but it just shows you the various ways that spin-off from NASA technology has been used by companies to help the ordinary humans of the Earth, whether it's a wireless alarm, a food processing control, water purification system, and so on. The solar powered electricity, it's numerous that we can talk about as a spin-offs. So when someone says, why are we spending money to go to space? I tell them, if you don't want to spend money to go to space, don't use your phones, don't fly, don't listen to and watch TV, because everything is a result of space technology. So we have visited a number of objects in our solar system. Humans have landed on the moon, even though there is a small group who believe that we have not. but we have landed on the moon. And then we have landed a robotic spacecraft on various objects in the solar system. We've landed on Venus, didn't last for a long time because of the high pressure. We've landed on Mars, we've landed on an asteroid called Eros, on Titan, another asteroid called Ikowaka. Then the European Space Agency landed on a comet nucleus called Comet 67P. And also, I think last year, NASA briefly touched down on a comet called Bennu and is bringing back samples. So we have landed on a number of objects in the solar system. This next slide is an ISO. I'm not here to actually go through each of these diagrams, but just to give you an idea of how many of the planets and moons in a solar system that NASA, ESA, ISRO, Japan, China, Russia have all explored. Each of those orbits is one satellite going around. And of course, the moon and the earth takes the pride of place. But Mars, we also have sent a number of objects and satellites to Mars. This is the future of space exploration. Right now, we are focusing on what is called low Earth orbit. The International Space Station is in the low Earth orbit. Then now we plan to go to the moon in the next 2-3 years. And then finally, by testing a technology on the moon, we would like to go to Mars, to other asteroids. And these are human missions. Then we also would like to send robotic missions to, say, something like Europa, which is a moon orbiting Jupiter. It's a very exciting moon because we know 99.9% absolutely sure that there's a huge block of ice which is covering an ocean underneath that. So we want to drill through the ice and test for some kind of microbial life form, maybe on Europa. So let's go and quickly go and talk about the moon. So this is the Earth's moon, okay? It's about 227,000 miles. I really hate trying to memorize numbers, and I don't expect students to memorize numbers. What they should understand is a relation with one to the other. So we have had 24 human visitors, out of which 12 have walked on the moon. There have been more than 100 robotic visits. Here are some of the landing places of the manned missions, which are the Apollo, and these the yellow ones, the orange ones are the robotic missions called the Surveyor, and the Chinese have the Chang, the Russians called Luna, and so on. So we have landed a number of robotic missions onto the moon. This gives you a idea of the size of the moon with respect to other objects in the solar system. I think the moon is the 5th largest object among the other moons in a solar system. Ganymede is the largest. But if you look at the size of the Earth and the moon itself, the moon is about 1/5 the size of the Earth. It's quite large with respect to its parent body. If you look at other moons of a solar system, they are not as large with respect to their orbiting planet. But the Earth is, and I'll talk to you about why we think that is so. So again, as I said, I don't believe in memorizing numbers, but some of them like to look at numbers. So I'm going to display some numbers for you to have a look at. But look at the last column, which is the relation of the moon to the Earth. That's what is important. So the diameter, it's 12,000 kilometers in diameter of the Earth. The moon is 3,000 odd kilometers. But this is what I want you to know. It's about the size of the moon is about 27% that of the Earth. That's what you can remember. Surface area, it's about 7%. The moon's surface area is about 7% of the Earth. In fact, the moon's surface area is actually smaller than the surface area of Asia. The volume is about 2%. The volume of the moon is about 2% that of the Earth. The mass of the moon is about 1.2% that of the Earth. The density, this is important, and remember this, it's about 0.6% that of the Earth. And this is important when we try to figure out how the moon was formed. The gravitational acceleration is about 0.16 that of the Earth. So you can jump higher on the moon than on the Earth. And of course, the escape velocity, it's easier to escape from the moon because of its low gravitational acceleration than the Earth. So it's about 0.2 of that of the Earth. Again, one thing about the moon I would like to tell you is the surface temperature. It varies from -200 degrees in the night or at the bottom of craters to about 120 degrees Celsius in the afternoon, especially on the equator. So there's a huge variation in the temperature, and that causes a problem when you land on the moon with instruments, with materials. We have to take that into account. Here's again another profile of the interior of the moon. We think there is a solid iron core, a partly melted outer core, and of course we have the crust and the mantle, very similar to the Earth. Surface features on the moon. If we just with the naked eye, if you look at the moon, you do see these dark patches. These dark patches are called the maria, which is sea in Latin. And they're actually the less heavily cratered area. It's a younger area. The highlands are more cratered, heavily cratered, and there's an older surface. When I say older surface, geologically, with respect to each other. Here are different surface features. As I said, you have craters on the moon. We have rays, which can be seen during a full moon. The rays are actually ejected from the moon when meteorites came and impacted the moon. Rilles are valleys from old lava depressions. And this is very important, this concept of rilles or rilles. These are actually lava tubes. And we think that if we can go inside one of these lava tubes, we can have a base inside the lava tube because the tube itself will protect us from the incredible dangerous radiation that hits the moon. So, right now we are planning to go to the south pole of the moon, but years in the future, we might think of going and trying to create bases in one of these lava tubes. Of course, I talked of the marias, and we have the ejecta. This one shows a very quick animation which will explain to you why the surface is lighter in color and then why we have these deep, dark areas. So when the moon was formed, it was molten. All the heavy elements sank to the bottom like iron and titanium, while the lighter materials came up to the top. The lighter materials are lighter in color. So when meteorites bombarded the moon, they broke through the crust and lava from deep inside seeped up to the moon, cooled down, and that's where we saw the dark patches. So these were formed after the highlands were formed. And you can see the difference in the colors. The white one is on the crust, and the dark moon rock is from the maria. Again, that's because it's lava which seeped up from the center of the moon, of the mantle, and solidified. That's why we see these two different features on the moon. One important thing that we have to figure out as you go to the moon is something called the regolith or the lunar soil. It's a loose layer covering the solid rocks on the moon. We have brought back some of the lunar soil. And on the moon, the regolith is it's a mixture of powdery dust and broken rock. And it's very, very sharp and is actually finer than grains of sand. And they're formed by the meteorites impacting the moon. The moon has a very thin atmosphere, almost negligible. We cannot even call it an atmosphere. So meteorites can come and hit the moon, and they bombard the moon and forms this regolith. And so, people typically talk about lunar soil, which is actually the finer fraction of the regolith. But in most cases, when they talk about the regolith of the soil, they almost mean the same thing. These are some of the building blocks of the regolith: silicon, aluminum, titanium, some iron. But these are the building blocks of the regolith. And this is important because we can use the regolith. Ed talked about 3D printing on the moon, and I can't go into that in detail. But we are going to use what is called in situ resource utilization. Use the resources on the moon to build habitat. So let's say we can build a habitat with some kind of a membrane. But because of the radiation, if you cannot block the radiation from the sun, from cosmic rays, we'll die within months. So we think that we can use this regolith, about 2-inch deep regolith. If you can coat this membrane, these habitats with this regolith in the form of a cement, it can block the radiation. So as I said, we don't want to, as Ed said, we don't want to carry everything from the Earth to the moon because it becomes very, very expensive. We want to make use of the resources on the moon. And some of the projects that I have funded in Florida is looking at how we can make cement from this lunar regolith and use it on the moon. This gives you an idea. Actually, the spacesuits, the lunar spacesuits were white in color. But once I landed on the moon, look at the color. It's become grayish because of all the lunar dust which stuck to the spacesuits. So this lunar dust or lunar regolith is going to be a major problem when we go to the moon. As I said, the moon does have an atmosphere. We really shouldn't call it an atmosphere. I think they call it a surface boundary exosphere. But it does have some unusual gases, including sodium and potassium, which are not found in the atmospheres of Earth, Mars, and Venus. And if you look at the Earth, it has 1 cubic centimeter, has about 10 to the 16 molecules. That is 10 followed by 16 0. But the lunar atmosphere, 1 cubic centimeter, has about 1 million molecules. So 1 million seems to be a large number, but actually is almost like a vacuum. And as I said, the atmosphere is made up of small amounts of atoms and molecules like helium, argon, hydrogen, and possibly neon and ammonia. But we don't know exactly the percentage and everything. They're still trying to figure that out. Here's an example of an observation made from the Earth. It is the moon at the center is blocked by the instrument, and you can see the sodium vapor all around it. Rayleigh is just an indication of the brightness. So near the moon, you have more sodium than far away. But this is just one example how you can figure out that the moon does have a very thin atmosphere. So those are the features of the moon. I'm going to talk to you about the formation of the moon. And this is where science comes in. So I'm trying to figure out how much time I have. So anything, any theory which explains the existence of the moon must take into account three major categories, three major characteristics. One is the moon has a low density, which means the moon does not have a substantial iron core like the Earth. Remember this. Second thing is the moon rocks contain very little volatile substance like water, which means that the moon's surface was heated more than the Earth. Why is that so? So anything that we explain for the formation of the moon have to take that into account. And the third thing we need to take into account is look at the abundance of oxygen isotopes, okay? They're very similar on the Earth and the moon, which means that the Earth and the moon were formed almost at the same distance from the sun. The moon was not found further away from the Earth. So when I talk about the 4 following scenarios of how the moon was formed, we need to take into account all these three major observational criteria. And if it doesn't explain it, we need to ignore that hypothesis. So let's start with something called the capture. So in the capture, what it is, they thought that the moon was formed somewhere very far away from the Earth. And then as it came close to the Earth, it was captured by the Earth. But scientists believe that it is a remarkable coincidence that the moon was exactly at the same place at the same time to be captured. Also, it does not explain the fact that, that the composition of the moon and the Earth are very similar. The composition of the moon is very similar to the composition of the mantle of the Earth. And if that's the case, then it shouldn't have formed that far away. And actually, one of the students is playing with the screen. It shouldn't do that. The second one is called fast rotation. And the idea was that the moon, the Earth was spinning very rapidly in the past. And as it spun very rapidly, a part of the Earth broke and formed the moon. But we have no evidence that the Earth rotated that fast in the past. And second of all, if the moon was formed directly from the Earth, the density of the moon would be the same as the density of the Earth. And that's not the case. It also does not explain why there are few volatile substances on the moon than the Earth. So we ignore the hypothesis of fast rotation. The third one is called co-accretion, which means that the Earth and the moon were formed from this disk of dust and gas going around the sun. So the Earth was formed and then the moon was formed from the remaining material, and it's going around the Earth. Again, the problem is that if the moon was made from the same material, why does it have a less density? Okay, that doesn't explain that. Also doesn't explain the fact of the lunar baking, extra baking of the lunar surface. So we have to ignore that hypothesis. Finally, the hypothesis which kind of matched up to the observation was something called the collision. And it seems that a few million years after the Earth was formed, a Mars-sized object came and hit the Earth. And it actually stripped the mantle of the Earth, which later formed the moon. And now that explains why the crust of the moon has chemical composition very similar to the mantle of the Earth. It also explains, and I'll show you in a later slide later on, why the moon was had that extra baking. Why was there more heating of the lunar surface? And I'll come to that in a second. Computer simulations also show that a hit by an object about 1/3 the size of the Earth resulted in the moon. So we now believe that the moon was formed by a collision. Moon's orbital dynamic. We know the moon takes about 27 odd days to go around the Earth, and it takes 27 days for the moon to go once on its axis, which means its spin and its evolution on the Earth is the same. And that's why we always see one side of the moon. We see what is called the near side of the moon. And the reason is tidal locking. Because of the gravity of the Earth, when the moon was formed, it was very close to the Earth, it was spinning very fast, but the gravity of the Earth, which is the tides, actually slowed the spin. If the moon was spinning faster than it is going around the Earth, it was slowed down by the gravity of the Earth, or vice versa, if the moon was spinning slower than its evolution around the Earth, the gravity of the Earth sped it up till it came into equilibrium, and now we have the moon almost showing the same face to the Earth. So we have what is called the near side and what we call the far side. The far side is not the dark side. The far side of the moon does get sunlight. Okay, it's just some misnomer that we have to blame Pink Floyd for his song Dark Side of the Moon. But the near side is what we see all the time, and the far side we don't see because of the spin. But look at the two pictures. Look at the near side. The near side has more Marias, more seas than the far side, which means the far side's crust is thicker than the near side. Because if the crust is thick, when meteorites came and hit the far side, it did not break the crust and did not allow lava to seep out and solidify. So you have very few seas on the far side. And why is that? And here's a quick animation to show you. So as I said, when the moon was formed, it was molten and was very close to the sun and was spinning rapidly till it was tidally locked. So you had one side of the moon always facing the Earth. The young Earth was very, very hot. So because it was very hot, it heated the near side of the moon more than the far side. The far side cooled faster. Because it cooled faster, the crust was thicker. Because the crust is thicker, meteorites could not penetrate the crust as much as the near side. So that's one of the explanations why we see very few Marias on the far side of the moon. And this is a present picture of the moon taken by NASA a few years ago. Look at the high resolution. Here's, I'm going to show you a very quick video of Earthrise as seen from the moon. This was taken by a Japanese a spacecraft called Kaguya, which I think means something. I forget what it means. It took a picture. It went very close to the surface of the moon, and it took a video. And here's a small a video of that video from the spacecraft looking at the Earth rising as seen from the moon. And this is real. This is not Photoshop. This is not an animation. So here's the moon.
Kaguya moves toward the South Pole on the far side of the moon. the blue Earth has appeared from the horizon.
So this is
the
actually Earthrise as seen from
captured
the
by the telephoto camera.
So this goes on, and instead of time, I'm going to stop it. But look at this. Look at this picture of the moon. And I've been working with a number of astronauts. And the first thing they say is that when you go up into space and you look down on the Earth, everything changes. They do not see boundaries. They do not see boundaries of countries. Their life changes. And I wish all of us could actually go to outer space and look down on the Earth, because it'll make us more calmer. It'll make a world a better place. But it'll take some time. As I said, tomorrow, you're going to have the first civilian crew being launched into space. So that's a start. And I don't think that the students right now watching this presentation will get a chance to go to space. But the school students right now, students on the 4th, 5th, 6th standard, they are the ones who will be going into space and going to the moon and going to Mars and so on. So quickly switch to figuring out search for water on the moon. Now this topic will take a couple of hours to talk about. So I'm going to briefly talk about 2 or 3 slides. It all started with the Chandrayaan mission. I forget which year it was, something in 2008 or 9. But anyhow, there was a NASA instrument called M3, Moon Mineralogy Mapper, on the Chandrayaan mission. And it actually reflected infrared waves, and infrared waves was absorbed by different elements, including water. And what you see on the right-hand side, on the top, on the north and south pole, you see a lot of blue, that's the water. The reddish in the center is actually iron, I think. But this shows that there is a lot more water in the north and south pole. And this was first discovered by the Chandrayaan spacecraft. Unfortunately, all the spacecrafts in the early 2000s, the instruments that we had, we could not detect whether the molecule that we see is hydroxide, which is HO, or whether it's H2O. So all this information that we got in the early 2000s, we were not sure whether it's hydroxide or H2O. But recently, SOFIA, which is a infrared observatory, they detected H2 molecules, because now the instruments are good enough to actually to distinguish between hydroxide and water molecules. So they have seen water molecules in a crater called Clavius near the south pole of the moon. But that's not enough. When I say they discover water, it's not much. In fact, the amount of water that you have, water molecules that you have out there is 100 times drier than the Sahara Desert. So we talk about, finding water on the moon. Just please note, we're not talking about, puddles of water or ponds of water, we're talking about water molecules. But we know that we think that near the south pole of the moon, in the craters, there is water in the form of ice. And that's where we can get most of the water. So there is one crater called the Shackleton crater. And again, as I said, I don't remember numbers. So it's about 21 kilometers in diameter, 12 miles diameter, and couple of miles deep. And inside this crater, very little sunlight reaches the floor of the crater, because the moon's axis is tilted by a couple of degrees. So as the moon goes around the sun, if there's something deep in the crater near the south pole, very little sunlight reaches it. So if there is ice in these craters, they're not melted by the sunlight, and we think there's a lot more ice in the craters on the south pole of the moon. So that is exciting, because there's more. Here's another one which shows all the blue, shows all the ice that we think are in the craters of the moons near the South Pole. That's why we are trying to land on the South Pole, because we want to be close to water, because we can use the water to break it down to form oxygen. We can use to breathe. We can use the water for the daily use, and so on. That's why everyone wants to land on the South Pole of the moon. So where does this water come from? The water came. It could have come from comets. Now, comets are basically dirty ice. So because the moon has almost no atmosphere, when the comets hit the moon in the past and it deposited ice, especially in the craters, if the comet hit the surface of the moon, the water would evaporate very, very fast. But because it landed in the craters, ice remained, and there's no sun air reaching. So that's where we think a lot of the water in the South Pole, in the craters, come from these comets. But the water molecules that we find near the equator, on the other parts of the moon, can come from two ways. One of the way is that the solar wind. The solar wind is a stream of energetic particles from the sun traveling about 1/3 the speed of light. It's basically a hydrogen atom with an electron. It's a proton. When they come and when they interact with the rocks on the moon's surface, about 45% of the rocks have oxygen with other minerals. So these high-speed particles from the sun, they break the oxygen bond, and then you get oxygen atoms. So if you have oxygen atoms and then you have the hydrogen atoms from the sun, they can combine to form hydroxide or water. So that's one way how water can form, is from the interaction of the solar wind with the lunar surface. Another one which recently found was from meteorites hitting the moon. And here's an animation. And this animation will show, so this is a regolith on the lunar surface. The regolith is about a few inches deep. And when meteorites came and hit the moon, it actually, so here you go, animation of meteorites hitting the moon. And then this is going to show you, so here's the impactor, and you have a 3-inch deep dry regolith, and below that you have hydrated soil, where you have the water molecules. So when these meteorites hit the moon, there's a shock wave. The shock wave travels down to the hydrated soil, releases the water molecules. And then there was a spacecraft called LADEE. It was detecting this hydrogen and water molecules. They detected these whenever there was a meteor shower on the Earth. They found there was an increase in the water molecules in the moon's atmosphere. So they think that these meteorites do hit the lunar surface, penetrate down because of the shock wave, releases some of the water. And here's something to think about as people go to the moon. Okay, so we have all these different craters on the South Pole of the moon, and you're going to have different countries going to the moon. The problem is that if you go to inside the craters, it's dark. There is no sunlight. If there's no sunlight, how will you power the rovers or wherever it is going to go to the crater? So because there's no sunlight reaching, so are they going to have nuclear power, or maybe use mirrors to get sunlight? So what most people will do, whether it's NASA, whether it's ISRO, whether it's Japan, China, there are peaks alongside the crater. They're called peaks of eternal light. And in these peaks, you have more sunlight because they're at an elevation. So you would like to form the bases in these peaks. And when you have the bases in the peaks, you can send rovers down to the craters to collect the ice and bring it up. Now you have to figure out a way to power the rovers, but that's another different story. So these peaks of eternal light are going to be the places where we think most countries will try to have their own bases. So I'm going to switch gears. I think I have about 10 more minutes, and I'm going to talk about the Artemis mission. So NASA has this Artemis mission to prepare for Mars. We wanted to go to the moon because it's close by. We can reach there in a couple of days, and if something goes wrong, we can send astronauts or robotic spacecrafts. To go to Mars, minimum of 6 months. If something goes wrong on Mars, it'll be impossible to send help quickly. So we want to test technology on the moon and then go to Mars. Okay, so how are you going to go to Mars? These are the different things. We have to have towers, launch towers. You have to build launch towers. You have to build a rocket. And this rocket is called the Space Launch System. NASA is almost finished with the rocket. It's going to be the most powerful rocket in the world. We have what is called the Orion, which is going to carry a capsule, which is going to carry the astronauts. The Gateway is going to be a small space station orbiting the Earth, of the moon. But that is one thing which is going to cause a problem because we don't have the funds for it. Lunar landers, we're going to have the idea is that for astronauts from the Earth to go to this gateway and from the gateway on a lunar lander land on the moon. And then we need to have new spacesuits to explore the moon and Mars. So NASA has done all these things. And I'll briefly talk about each of them quickly. But on the interest of time, because I don't think I have a lot of time left, I'm going to talk quickly about the rocket, but I'm going to show you a video of the rocket to show you how complex it is and of the various parts that the rocket has. It's called the Space Launch System. But the main fuel for this rocket is used in what is called a solid rocket booster. It's a solid fuel, and 70% of the thrust that you require to take the rocket off the gravity well of the Earth comes from these rocket boosters. And these are 5-segment rocket boosters, solid fuel, which means that once you start burning the fuel, you cannot stop it. But if you have a liquid fuel, you can manipulate the amount of liquid that goes to the engines, you can control it. But a solid fuel, once you start burning, you cannot stop it. So but they are more powerful. Each of the solid rocket booster is 17 stories tall, and it generates more thrust than 14 4-engine jumbo jets. Think about that. Each booster will generate more thrust than a 14 4-engine jumbo jet. About 170 feet in length. For people who like numbers, 12 feet in diameter, about 1.6 million pounds. It operates for about 2 minutes, 126 seconds, and they provide more than 75% of the total thrust required to take the rocket off the Earth. And so this is the one, this actually explains the whole rocket. And it shows you the various part of the rocket and how complex it is. So you have the Orion spacecraft, which is the spacecraft, the launch abort system, we'll talk about that. And then the space launch system, which has the various. So here's the launch abort system that is just connected to the Orion capsule. If something goes wrong during launch, the launch abort system can carry the astronauts away. Here's the Orion crew module, which will carry the astronauts. Here's a service module, which will have the electricity, the food, the power that you require to power the Orion. This is a stage adapter adapting the Orion to the rocket itself. This is the propulsion stage. Again, stage adapters for the propulsion to the main rocket. There are various parts of the rocket. Just to show you how many parts there are. This is a liquid oxygen tank. Look how big it is. There's some humans next to it. This is a liquid fuel. This is a tank between the oxygen and the hydrogen, which is a liquid fuel. It's called the intertank where you mix. This is a liquid hydrogen tank. Again, see how big it is compared to a human being. Here's the engine section. So there are 4 or 5 engines. This is called RS-25 engines. There are 5 of them. These are rocket boosters I talked about. This is a testing being done in Utah, in the United States. So as you see, it's a very complex rocket, and you need to test. I'm going to just show you one test of the liquid fuel tank. You need to test and test and test and test because we're carrying humans. We cannot afford to have some mistakes. So here's one of the tests of the rocket structural design. So they're going to actually push the structural beyond the limits that the rocket will face to see what's going to happen to the fuel tank. So those are the engines of the rocket. And that the orange one is the fuel tank. Here's the fuel tank, which has a liquid hydrogen and liquid oxygen. So now they're testing this fuel tank. But they're going to shake it, move it to mimic the conditions of a launch and to see how much vibration and other forces it can withstand. But they went beyond what they're going to face during a launch. They pushed it till it failed to find out what's happening. So look at it. Look what happens when they keep on pushing the limits. Okay, it pops and twists like a soda can. But this is beyond what they're going to experience. But what I'm trying to get to is that they always try and test things out. This is the Orion part, the Orion constellation, the solid rocket, the launch abort system, and so on. I'll show you an animation of the what is inside the Orion crew capsule. This is built by Lockheed Martin. So you can carry about 4 passengers. There's a glass cockpit. And there's a radiation shelter. So if there's some intense radiation from the sun hitting the spacecraft, they can retreat to the shelter. There's the environmental and control and life support system. Of course, you need to exercise. If you're in microgravity for a long time, your bones become weak, so you need to exercise. So you have an exercise machine and a water dispenser. So they've thought about everything. There's a zero gravity toilet for both genders. And these are expensive. These toilets could be almost $1 million to build. So that's the Orion capsule. That's what the astronauts are going to be in this capsule. Here's an example of the controllers now. So we used to have analog controllers. Now everything is going to be digital. So the launch abort system, that's a safety precaution that we have. If just before launch something goes wrong with the rocket or just after launch, then this launch abort system is a smaller rocket atop the Orion, which will carry it away to safety. And this is an animation of that test. We had a real test, and on the interest of time, I cannot show you the actual video. It's about 5 minutes, but this is an animation of that test. So it's a small rocket. They have the Orion capsule on the top and the launch abort system. So if something goes wrong, then what's going to happen is that the rocket on the top will pull the Orion capsule away from the main body of the rocket. And that's what they tested. So I live in Titusville, which is across the river from Kennedy Space Center. And I can see all the launches from my home. And I did see this test launch about 2 years ago. It was very successful. But look, it has taken the capsule away from the main rocket, and then the capsule will disengage from the smaller rocket, and with the parachute, it will land on the earth or on the ocean, mostly on the ocean. So this is the animation. And here is the capsule that will land on the ocean. Parachutes will come out and will land on the ocean. Okay, so that's thing. I'll skip the gateway because we have no idea when this is going to take place. I'll skip it because we don't have too much time. I want to talk to you. We support a number of student experiments. To give you an example, NASA has given funds to 3 companies to land unmanned rovers or spacecraft onto the moon. One of them is called Intuitive Machine. They're going to land they're going to fly 5 payloads onto the moon. One of the payloads are built by students from my organization, They are the Embry-Riddle Aeronautical University. And what they have built is, these are by undergraduate students. They've built what is like a CubeSat. And it's a box, and they have cameras on all 5 sides. And what they're going to do is, when this intuitive machine lands on the moon, just before it lands on the moon, the landing of that intuitive machine is controlled descent. Before it lands, this box, this cube, will be thrown from that rocket landing onto the moon. That box will land free fall, will land onto the moon before the rocket lands. There are 5 cameras. The cameras on all 5 sides. So it doesn't matter how the box hits. It's going to hit the moon and take a video and picture of the moon, of the rocket landing on the moon, and send it back to the Earth. This was all done by students, and we are hoping to launch this hopefully at the end of this year. But what I did was I gave them funds to test it on a Blue Origin flight, to test it for loads, for shock, for vibration, so that they know that when they go on this bigger rocket, that spacecraft, that CubeSat or that payload will be safe. And that's where they're going to land. We're also going to have human landers to land on the moon, and here's where politics is playing a big role. So NASA had selected 3 companies and give them initial some funding to come up with a design to carry humans to the moon from the gateway. One was Blue Origin, one was Dynetics, and one is SpaceX. And then a few months ago, NASA chose SpaceX as a company that's going to build the human lander. Unfortunately, Blue Origin has sued the government that they think that theirs was also worthy. So now the human lander contract has been stalled until the courts come to a decision. So here you have politics playing a big role in the future of space exploration. Spacesuits, we'd have to have new spacesuits because the old spacesuits were not good enough for exploration. The spacesuits they use right now outside the space station is called the Extravehicular Mobility Unit. And they were designed for floating spacewalks, not actually on the moon. And I'm going to show you a very quick video of astronaut Harrison Smith tumbling onto the moon as he was trying to pick something up because the spacesuit were not flexible enough when you're bending. And imagine if that spacesuit was torn, he would have died because all the oxygen that's inside would have seeped out. All the lunar dust would have gone inside. So we need to have very good spacesuits which are more flexible and also more durable. So NASA has come up with 2 different spacesuits. One is for extravehicular activity like a spacewalk, or walking onto the moon. Another one is what's called the survival system, which is if you're in the spacecraft and going to the moon. So 2 different ones. And they're they have different sizes. They are interchangeable. The gloves are different. The arms are different. The legs are different. And they are more flexible. You can bend down and so on. So these are the new spacesuits that NASA is going to be used. So I'm going to finally end, because I think I'm running short of time, I'm going to finally end with a couple of slides, the problem with moon dust. And this is one of the Apollo 7 commander. He said that, I think dust is probably one of the greatest inhibitors to a nominal operation on the moon. I think we can overcome other physiological or physical or mechanical problems except dust. So here you go. I showed you this picture. This is a picture of Scott's dusty Apollo 15 spacesuit. Dust all over. Okay. So because it darkens the surface of the spacesuit, it increases the heat transfer, so it becomes hotter. The dust is very, very fine. And I know for sure that these helmets that the Apollo astronauts had, the glass of the helmets, when you have those dust on the gloves and the dust on the helmet, when they were trying to wipe the dust of the helmet, it actually kind of, I didn't crack, but etched the glass a bit. They're so fine. So these dust particles, if they enter your body, you're going to have lung cancer and so on. It has negative effect on coatings, on seals, on lenses, on solar panels. So anything that you build onto the moon, that take to the moon, have to take all these things into account. Even wiring. As I said, damage to astronauts' lungs, cardiovascular system, and also there can be something what is called spacesuit arcing because of dust streams exposure to the space environment. And finally, just to show you how difficult it is when you're landing, and because the regolith is so thin, when you land, there's so much of dust that is blown away. This is actually an image, a video of the Apollo 15 landing on the moon. And alongside, we take another video taken later on of that same area of the moon. And I want to show you how much dust is being blown away. So there he goes landing. You can hear him talk.
-6. -5, 100 feet at 5. 9% fuel.
On the right is an image from the lunar LRO
60 at 3.
showing the same area.
50 at 3. Cross pointers look good.
Now look all this dust being blown. See, on the left-hand side, look at all the dust. I can barely see the surface.
25.
Can barely see on the left.
7% fuel. 20 at 1. 15 at 1. -1. -1. 6% fuel. 10 feet -1. 8 feet -1. Contact. Man.
So do you hear?
The Falcon is on the plane ahead.
You hear the end what he said? Bam. Because they couldn't see the surface properly and they landed very properly. In fact, they actually landed, look at it, this was taken by another picture. The module was very close to a crater, very close. And look at it as it's inclined a bit because they couldn't see where they were landing. So any future missions going to the moon, I have to take that into account. And if you have, as you're landing, if you have other bases close by or like other instrument close by, the plume which is being blown away by the moon, by the lander, is that going to affect the instruments and on any settlement very close by? So I can talk a lot more about these effects of the moon because that's the research we're doing here in the institute. But I think I'm going to stop here now because I gave you an idea of what the moon is, what a problem is, and how NASA plans to go to the moon. So I'm going to stop sharing my screen and I'll stop right here. I don't know whether we have time to take questions now or later on, but I'm willing to take questions later on by email.
Thank you, Jaideep. Am I audible, please?
Yes.
Thank you, Jaideep. That was a brilliant presentation. We all now understand why you are one of the most sought after speaker from NASA. That was a great education for all of us. Thank you so much for this. Ladies and gentlemen, now I take pleasure in requesting Mr. Sudhir Kumar, Director of ISRO, who has kindly consented to give us special remarks. Mr. Sudhir Kumar was elevated as Director of the Capacity Building Unit of ISRO very recently. Mr. Sudhir Kumar is a mechanical engineer and then did his post-graduation in industrial engineering. He joined ISRO in 2000 and has been a core team member of realizing Asia's largest solid rocket propellant plant at Sriharikota. Mr. Sudhir Kumar has been managing vendors for the past so many years, and his involvement in building the various projects of ISRO has been very, very vital. Mr. Sudhir Kumar was deputed for Space Studies Program at International Space University, Austria in 2011. May I now request Mr. Sudhir Kumar for your special remarks, please. Over to you, Mr. Sudhir.
Thank you, Mr. Giri. It's an amazing talk. I was all through. I was spellbound. Probably, I think I don't have words to say what Dr. J.D. Mukherjee has spoken about. Probably, I think after listening to him, probably I request him to deliver one talk exclusively. One international space seminar is conference is going on, which I am planning for exclusive student session. Probably a couple of days to come. Probably after listening to him, I think that I should request him to deliver a special talk. Okay, that I will just get connected through. No, it's amazing because especially in India, such kind of experiences and such kind of talks will motivate the students to improve the appetite of learning more. Probably, I think our students probably never get exposed to first level of such kind of talks, except going through the NASA sites or NASA documentary. It was amazing. I think the students who are watching are blessed. I think the entire credit goes to Mr. Giri. That's what I think. You have created a platform and you have created an opportunity for the students, including adults like me, to listen to such kind of wonderful talks. I'd be very grateful, but of course, ISRO of late started interacting with the international the platforms with people like Dr. Jaydeep. We had Moon Village Association, somebody creating a platform for having such kind of talks, and ISRO per se opening the doors now even for the student community, student trainers, or the agencies and the let us say NGOs who are into the STEM activities. Probably such kind of cooperation will inculcate. I could surprise to see some of the students, undergraduate students, developing a full-fledged CubeSat, which will be deployed in the Artemis mission. Artemis is such a wonderful mission with a lot of scientist involvement. It is amazing to note a couple of students with the help of Dr. Jagdeep, etc., they could make a full-fledged CubeSat. I think that should be the spirit somebody has to derive. I request all the students to adopt such kind of good practices. ISRO is always for student missions. ISRO is always supporting to encourage the students for student SAT development. And there is a full-fledged program, student SAT development through ISRO's URSC, URO Satellite Center. Only thing is you may have to come through your colleges for making such kind of proposals. I am amazed. I thank again for sharing remarks, of course. That is the ultimate thing what I could do. And especially listening to Dr. Jaydeep. Thanks a lot, Mr. Giri. Thanks a lot. And all the best for the students.
Thank you so much, Mr. Sudhir. That was very nice of you to have pitched in. And with somebody from ISRO, so senior like you, I'm sure the students are going to be benefited. Thank you so much. Now, may I request Abhirami to introduce the panelists? Please.
A special welcome to Mr. Manoj Pillai, a Supreme Court advocate. He is the managing partner of Manoj and Chitra Law Firm based in Trivandrum. His areas of practice are property law, European Union law, international law, competition law, aviation regulatory law, intellectual property, and other related laws. We feel honored and thank Mr. Manoj Pillai for joining us today. We welcome Mr. S. Balagurunathan, a science teacher with a wealth of experience spanning more than 3.5 decades. He is a retired headmaster of Neyveli Government School and has written the chemistry book for 11th class. He has won the prestigious NCRT Award and Times of India Award. He is an advisory member in Explore the Space. He has collaborated with ISRO scientists to conduct various webinars. It is an honor to have you, sir. Thank you for joining us today. Ms. Akriti Singh is a student representative from Dubai, UAE, who is studying aerospace engineering in Dubai College. Her field of interest is technological advancements in space travel and exploration. We are pleased to have you, ma'am.
Over to you, Mr. Balagurunathan, please. Mr. Balagurunathan, your special remarks, please.
DV, do you see him in the chat? Are you able to unmute him? I can't find his name.
Yeah, Mr. Balagurunathan, over to you, please. Yes, sir. Yeah. Sir, please.
Next agenda என்ன சாதிக் பேசுவோம் ரைட் இல்ல so far we attended a beautiful and wonderful session and this can give lot of benefit to the students community. Yes ma, any query ma, you can ask.
Hi, yeah, I'm the student representative from Dubai. I have a little thing that I'd like to say too. Can you hear me?
Please ask ma, any query?
Yeah.
Akriti,
What is your doubt?
How are you doing? Mr. Balagurunathan, can I request you to continue with your remarks, and then Manoj, and then Akriti. We will have to go a little fast.
Yes sir. Yes, sir.
Please
Yes, sir. Once again,
proceed, Mr. Balagurunathan. Yeah.
Yes sir. Once again, thanks for the privilege. Space technology is no longer considered as a high-tech venture whose costs make it an irrelevant luxury for a developing country like India. In this way, we thought for a few decades ago. But the benefits of the space research have great relevance for the developing countries. Satellites have become an integral part of the nation's infrastructure. The space program of various nations have led the development of the new technology and new materials, and also helped other areas of industries to improve very high precision and very fast real-time computation, especially in the case of rendezvous operations. New materials to provide lightweight miniatured equipment and for such a special application as heat shield, micro miniatured electronic circuitry, special monitoring equipment to keep a close and continuous watch on the functioning of the human and other living being in space, and even various infrastructure, various instruments on the board space vehicle have all lead to the new materials, processes, techniques, and technologies which are now finding use in other areas. After revolutionizing communication through satellite, space programs accelerated natural resource management, study of agricultural potentials, weather monitoring, and disaster management. Furthermore, the spin-off from the space technology find application in the fields ranging from the food storage to open heart surgery, from fishing to automobiles. It is clear that the space technology and science have made rapid strides in the past 3 decades. Now, regarding the recent research, how important is the astrobotany research for the future space explorations? That is one question arise. That is astrobotany. Biogenerative life support system supplement calorific intake with plant in sustainable plant growth is tested. Space gives an immense help for astronauts' mental health. The astrobotany gives the immense help for astronauts' mental health also. Nowadays, the fast development is possible because of digital acceleration. The existing pandemic situation is unlocking the digital potential throughout the world. Now we landed into the 5.0 industrial revolution. In this circumstance, if you search a career in space industry, lot of openings are available globally. Now, what are the available facilities and available job opportunities in India mean? Now, India, ISRO is recruiting the people in 3 ways. In 3 ways appointment at ISRO, 1/3 in R&D, 1/3 in fabrication, 1/3 in project operations. Project people are launching the satellite and space stations. They are getting the name and fame. Now, accessories are also produced by various companies. Hindustan Aeronautics Limited, they are producing light alloy structures. Mithani, Hyderabad, solid motor segments. Kerala, titanium sponge plant from beach sand. Bay Forge, ring rolling. NFTDC Hyderabad, vacuum furnace engine. Mumbai, PF 108 resin. Mithani, ultra high strength steel material. Bharat Forge Chennai, titanium alloy. BHEL and L&T aerospace casting. NFTDC, samarium and cobalt magnetic materials. What are the requirements to enter into the space industry mean? After completing the formal procedure, now you should have some additional qualifications. That is not the basic requirement, but you can enter into the project area if you are well versed in artificial intelligence, machine learning, robotics, electronics, augmented reality, virtual reality, 3D printing, coding, Python, and some of the cutting edge technology. These are all some added advantage. You can enter into the project area by qualifying all these things. Exploring STEM career. Now, the space research and the space formulations require a versatile knowledge in science, technology, engineering, and mathematics that lead to STEM career. In the STEM career, what happens mean, suppose if you are well versed in this area, mean you can get STEM career in the space research organization also. What are the future prospect mean? Now, instead of launching mega satellite to the space, now we turn to launch the nano satellite. Nano satellite of the order of 1 kg to 10 kg, it looks like a shoebox. The lifespan can be extended from 6 months to 5 years. Now, this gives a lot of benefits. This is economic. Moreover, this can be easily fabricated. Now, this fuel economy is also ensured by launching these things. The maintenance is also easy. In this year 2020-21, the total satellite launched so far is equal to the satellite launched so far. Space traffic system is also developed by NASA. If you want to maximize your potential, then you have to follow, that is U power 4. What is U power 4 mean? Now write down the formula U power 4, YOU power 4. In YOU power 4, the first U, use tech. That is the first U, use tech. The second U is upskill. Upskill means that is the need of the hour, upskilling. The third U is upgrade. Upgradation is the order of the day. The fourth U is update yourself. Update yourself means that is the updation is the survival of the fittest now. Then only you can fit into a project. Let me say you have to maintain the 4U. Now regarding the space industry, the space industry is working on four verticals. The four verticals of the space industries. The first vertical is the space applications. Already the speakers have given a lot of information regarding the space applications. That is, space application enables telecommunications, Indian remote sensing, that is remote sensing, meteorological environment, land use, land cover, and water resources, etc. Space infrastructure. Sir, சொல்லுங்க sir. Sir. Why, sir? என்ன sir? முடிச்சுக்கிறேன். Space infrastructure, space transportations, and capacity building. On this four verticals, like you have to enter into the space industry. Like for that, you can qualify the proper degree. Then you can enter into the space industry. The students can plan your future. Suppose you want to enter into the space industry, based upon this requirement, you have to qualify yourself. All the best, students, and stay with us for further program. Now we can learn a lot regarding the space science in future. Thank you, and thanks for the privilege once again.
Thank you, Mr. Balagurunathan, sir. Manoj, can I request your remarks, please? Can I request Mr. Manoj Pillai for his special remarks?
Hello.
Yes.
Am I audible?
Manoj, thank you. Yes.
Thank you.
Yes.
I was unable to unmute myself. I think the host was not permitting me to unmute. That was the reason. Anyway, thanks for the privilege and an opportunity to pitch in a lawyer in a forum of a space technology, because we get an impression, or people rather get an impression, that lawyers are required only when we are talking about civilians, or when countries are having disputes, international disputes. And rightly, Mr. Jaydev has been pointing it out, when you look from the moon, there is no boundaries. So we are talking about a law for the whole universe, because here the laws are between the humans and the aliens. So we are talking about a different type of space law. We are talking about a law where we are talking about how our space flights are going to be monitored, even though we don't have boundaries when you look from moon. But the problem is each country is trying to equip themselves in sending space flights and getting into the space as one of the business destination. As Her Excellency has been telling, Uganda is also taking steps, just like any other country like USA or India, into space technology, because we are finding space is becoming the place from where more business opportunities are available. So we used to say, stay locally and think globally. I think that phrase has no relevance in future. Now we have to say that you stay locally, or rather stay in the moon, and think in a universal manner. Think from a matter, not from Earth as one of your business destination, but as galaxy as destination. Because yesterday I just got an article which was talking about, there was a boy, a Russian boy, who claims himself that he was born in Mars in his previous birth, and he has been talking to people, and he has been trying to convince the people that he has a life, a previous life in Mars. So we don't know what is the reality. As Mr. Jaydev was trying to say, that we are trying to explore. When you are trying to explore things, we are looking into new ventures, new opportunities. So as students, we have to look into the concept of how we are going to use the opportunities available with us in a very unified manner, and in a manner where we can not only look into concept of using our engineering degree or our accounting degree or social understanding about botany or biology. As Mr. Gurumurthy was telling, every spectrum of our education is going to be useful when you are going to explore the space. It is not that limited to only this physics person or the mathematic person has got a mileage when it comes to a business opportunity in space. So even as lawyers, I find nowadays, as rightly been told by there are a lot of things which are happening. There are a lot of MOUs being signed between the private players and the government in promoting, and even they're trying to chip in Moon as a destination where you're going to put in more infrastructure. So it's going to be a lot of business infrastructure documents are going to be in place. Not only that, when there is going to be infrastructure documents, there are going to be conflicts, because as he has rightly told, from tomorrow we are going to have the first civilian population going to target the space. So we need laws, and laws are required. Even space law is going to be a developing law. And just like we have internet and information technology law, and these information technology are happening only because our involvement in the space technology. If we have not sent our satellites above our Earth, we would not have had weather reports, we would not have had telecommunication availability, nothing would have happened. So end of the day, everything is happening because of our exploring the space and finding out more and more avenues of business. And as been put forward, and the chances of how we are going to interact with persons who are well versed in space technology, in the industrial aspects, how we are going to involve more and more new products wherein you can try to use the space as one of the destinations. As rightly told, that is, might be the students who are studying in the school, might be making their destination, tourist destination, that they are planning to go for a honeymoon in Mars or in Moon. So that's the level of thinking we are looking at, and that's the way we are going to target our advantages we have. And we are going to even use the space as one of the areas where we going to look at our humanity as such, where we are going to benefit the human race. We are going to get into more resources. Of course, we have international regulations which says that you are not going to use the space for any nuclear warfare, or so we need to use even the, as I rightly told, even the nuclear power has to be used for peaceful purposes. So that's really permissible. So I would expect these students to use this forum and try to understand more and more about space and space technology and space law. And so irrespective of whatever faculty you are studying, this is going to be, the explore the space is going to be your launching pad to know the future of your capability of getting more and more job opportunities. And it is very interesting to know about something which we have not been told till yesterday. So every day you come across new concept, new information from the space. And I once again thank everyone who has been present here and who has been also coordinating with this event degree to make this as a great success. Thanks once again. Thank you very much. And I expect the students to make this as an opportunity to use this so that more and more such seminars come up, and we want the student population to see that space is going to be our next destination of our job opportunity. Thank you.
Thank you. Thank you very much, Manoj. Thank you for that. Thank you for your presentation. Uh, Ladies and gentlemen, I have pleasure in welcoming young and energetic Akriti Singh, a student representative from Dubai, United Arab Emirates. She is pursuing her aerospace engineering in the Dubai College. Over to you, Akriti, for your remarks, please.
Hello, am I audible?
Yes, yes, you are. You are.
I just want to share this PowerPoint while I speak. So good evening, my name is Akriti Singh and I'm currently a student at Dubai College. I have wanted to study aerospace engineering for as long as I can remember. So being able to speak on this platform is an honor. So a few years ago, I used to passionately read and watch dystopian movies and TV shows. One of them had an extremely deep impact on me. I would love to share it with you guys. Fast forward 100 years as Earth becomes unsurvivable due to excessive extraction of Earth's resources, nuclear wars, radiation, humanity is slung short into space station, which they have to learn to survive for 100 years. After 100 years, they try coming back to Earth, but yet again, because of the excessive amount of radiation, it's not possible. In addition, the space station also outlived its life cycle. Thus began the race against time to explore space to relocate fast. This truly intrigued me, and this inspired me to look further into space exploration and technology. I think that space exploration is one of the most difficult and complex endeavors of mankind. I find it incredibly interesting how scientists claim we've only explored 4% of the visible universe. After thorough research, I believe space exploration has one of the most crucial roles in terms of future for humanity as well as Earth. With a combination of human ambition to drive and to continue exploring with the constantly growing technology, the results are immense. The most recognized and influential of the first generation space pioneers are Tchaikovsky, Goddard, and Oberth. Tchaikovsky was the first mathematician to study in detail the use of rockets for spaceflight. He later wrote an article, The Exploration of Cosmic Space, which laid out principles of spaceflight. Goddard conducted much of his work in secret, after he started becoming interested in space exploration. And Oberth is widely recognized for his pioneering in rocketry. His work has been rejected multiple times, but it actually explained mathematical history and theory of rocketry. Anyways, over the past few months, the invention of production of space technology has not directly addressed more global problems like poverty or world hunger, but in development processes, there have been plenty of byproducts. So there have been a plethora of positive outcomes from all the money being invested. The main areas being healthcare, protection of planet and our environment, enhancing safety, and of course, scientific discoveries. In terms of healthcare, there has been positive outcomes on surgery, cancer, heart technology, and for Earth, of course, monitoring natural disasters, pollution, which ultimately helps us monitor climate change. Finally, the aim for space exploration is, of course, scientific discoveries. In addition, here are some more technical innovations which you'll probably see more in a day-to-day life, such as artificial limbs, solar cells, insulin pumps, tires, frozen foods. Now, my favorite part, the future of space exploration. As for NASA, and as mentioned before, they had the intention of going back to the moon to learn and explore, to ultimately understand what could support human exploration as they travel to Mars and beyond. As they build an Artemis base camp on the surface and the getaway to lunar orbit. The scientists' hard work to continuously observe and understand our planet and beyond will eventually lead to the answer of, are we really alone? In conclusion, since the beginning of space exploration on October 4th, 1957, space technology has been growing exponentially. From just being able to observe our moon and our sun to the furthest individual star ever, Icarus, located over halfway across the universe. The upcoming decades holds a great potential in terms of space exploration. I would like to end by reviving a famous quote by Edwin Hubble. The history of astronomy is a history of receding horizons. Thank you so much.
Thank you so much, Akriti. You summed it up so very well. We greatly appreciate your interest. Let's give a big hand to Akriti, the youngest of the presenter. Thank you for your participation. We look forward for more and more participation from United Arab Emirates and students there. Nikki, we will now wind it up. Can I request the participants and others to send questions to Jaideep? Is that okay with Jaideep? We find Her Excellency, Madam Grace Akelo there. Thank you so much, ma'am. Thank you so much for staying through the program. And our sincere thanks to the main force behind the entire event, Mr. Tim Dyer. Thank you, Tim. Ed, would you like to take questions? Or
So I'm not sure why Nikki can't.
The students
there
to send
she's.
questions?
So I think Nikki finally got unmuted. Go ahead, Nikki. I was going to answer for you, but go ahead.
Okay. So there were a few questions in the chat, and unfortunately we're running short on time, but I can bring up a few.
Nikki, Nikki, can we request Mr. Jaideep for his final remarks? Jaideep, can we request you for your remarks, please? Final remarks.
Yes, it was great talking to the students and listening to Akriti's presentation. We need more students like Akriti in this world.
Sure.
I think you'll go places. I'll be glad to take questions in the form of email.
Sure.
They can email me, but please know that I get hundreds of emails every day. So it'll take some time for me to reply back. As long as they say that they are from this webinar, I'll gladly answer the questions. But I enjoyed it. I did enjoy this whole webinar.
Thank you, Jaideep. Special thanks to Mr. Sudhir Kumar. Mr. Sudhir, we were able to get in touch with you only by yesterday evening, and it was very nice of you that you came in. May I request your remarks, please, your final concluding remarks?
I think only one word to say, that our cooperation is with you. Probably, I think we should have many more such kind of programs, many more such kind of eminent speakers to come onto the platform and educate. Our full cooperation from my side being I'm in charge of the entire outreach for the entire ISRO. My full cooperation is with you. Thank you.
Thank you. Thank you so much, Mr. Sudhir.
DV, I'm not sure you can. DV, I'm not sure you can see the screens, but I think Grace has a question.
Yeah. Do we request Her Excellency, Madam Grace?
Yes, thank you. Can you hear me?
Yeah.
Yes.
No, it's not really a question, but thank you for pointing it out, Ed. What I wanted to say was, I know that Dr. Mukherjee has got a lot of questions and a lot of emails to attend to, but in view of the level of interest, especially from students and some of the young people who are employed in various areas who are interested in space technology, space exploration, perhaps we should make a special allowance for us, for such people, so that if they write through the CEO of space, the current convener of this webinar, then this is my suggestion to them, that you write through him so that he, who has been able to link us up with Dr. Mukherjee, can continue this connection so that our questions don't get swamped down by all those other emails which he gets. And therefore, we continue to benefit from your wonderful, wonderful knowledge and experience.
Thank you so much, Madam Her Excellency. Thank you so much for this. Our special thanks to Supreme Court Advocate, Mr. Manoj Pillai, Science Writer, Mr. Balagurunathan, and the student representative from UAE, Ms. Akriti Singh. So it's good night from India and good morning to friends in United States. As you go ahead with your work, you're going to go to bed. So we all meet again. Thank you, Tim. Thank you so much, Jaideep. Thank you, Ed. Thank you so much for this. Thank you, Nikki.
All right. Thanks, DV and everyone.
Thank you.
Thanks,
Thank
DV.
you so
Thank you very
much.
much. Thanks, everybody.
Thank you. Thank you.
Thank you.
Bye-bye.
Okay. Bye-bye.
Thank you. Bye-bye. Bye-bye.